So Yoram is going to tell us about vortices and this.
Yes. Thank you. So I'm going to talk, I guess, about some work that I've done on dynamics of hydrodynamical accretion disks. And for this audience, I don't think I need to go through all the observational motivation, because I'm sure you're all familiar with it. I'll just say some of the interesting questions that we'd all like to know the answer to is, can hydrodynamical disks sustain turbulence by themselves? Can vortices form? Under what conditions do vortices form? Do they decay? Questions like that. So those are some of the things that I've been hoping to address. So I'm looking at hydrodisks. So just the cartoon, we have a star in the center, and we have an accretion disk around it. And I look at a little patch in the disk. This is in the shearing box approximation. So we just look in this box. And then in the shearing box approximation, there's a mean shear, a mean Keplerian shear. So there's a mean flow, and the shear goes like this. And so there's just there's a background shear. So I'll write the background shear is equal to minus Q, is the shear parameter, times x, y hat. So x is the radial direction, and y is the azimuthal direction. Right? So then I'll just explicitly write the equation. So I'm going to consider probably the simplest possible equations, the incompressible hydrodynamical equations. So I'll just write out explicitly what it is. It's just dt v plus v dot grad v. It's equal to minus the gradient of a pressure. And then there's other terms due to, so in the shearing box limit, we go into the reference frame of the center of the box, and it's orbiting with orbital frequency capital omega. So there's a Coriolis force, which is minus 2 omega cross v. And then there's also a centrifugal force. So it's basically an omega squared x term, but we only care about the difference in centrifugal force from here to the center of the box. It's just the omega squared dx times x. And so that's it, except we need to do something about the pressure. And so instead of having an equation of state, I just say that it's incompressible. Del dot v is equal to 0. So this type of incompressibility is typically good when motions are subsonic. In that case, it's typically the case that you can use the incompressibility approximation, although there are problems with this in disks. For now, my main justification is just this is probably the simplest possible equations we can explore sort of dynamics of accretion disks, I think. Okay, so in this system, there are basically two parameters. There's capital omega, so it's just a constant. Right? That's the orbital frequency of our shearing box. So the parameters are capital omega, the orbital frequency. And then there's Q, which is the shear rate. Shear rate. It's just really d omega dr, or d log r. And in a Keplerian disk, it's equal to 3/2 omega. But for what I'm going to do, I'm going to keep these separate because there are really two physical things going on. There's a rotation and there's shear. So it's worthwhile separating what these two effects are. Okay. So to consider dynamics in this type of disk, I'll go in a number of stages. First, I'll consider the 2D limit. I'll look at the dynamics in the plane of the disk. Okay, so in the 2D limit, 2D. So first of all, decompose the velocity into the background, which is minus qx y hat, plus u, which is everything on top of the background. And then actually in 2D, it's simpler, instead of dealing with an equation for the velocity, to write an equation for the vorticity. It's actually, in 2D, it's simpler. And the equation for, we define the vorticity as just the curl of u, so it's just the curl of the perturbation. And the equation for the vorticity is dt minus qx dy of omega equals minus u dot grad omega. What this says is the vorticity is just advected along by this qx, which is the background shear, and it's advected by u. So it's advected by the total velocity field, which is the background shear and the perturbed velocity field. And you note also that there's no capital omega in here. So in the 2D incompressible limit, the rotational effects go away. Like they're just not important. And, well, they're not important, they just don't appear. So you only care about the shear. And basically, this is the same dynamics as a 2D shearing flow with no rotation. OK, so now this looks pretty simple, but I'll consider an even simpler case, which is first I'll do the linear case, where we can drop this right-hand term. Right? So it's dt minus qx dy of omega equals 0. So this is really, it's almost a trivial equation, but I'll spend some time discussing it. So what it says is that the vorticity is advected by the background shear. So the background shear is like this. And so I'll plot contours of constant vorticity, omega. So let's say we started off like this, where the contours look like this. Then at later times, the shear is just going to twist these lines. So this is called a leading wave. Then the shear just twists them. It makes the lines like this. So now they're pointing in the radial direction. And then it points them in the trailing direction. And if you continue in time, it just it makes it tighter and tighter. So it just lines them more and more with the azimuthal direction. Okay. So this seems almost trivial. Now I'll look at this from a second point of view, which will be useful for what I do in a minute. I'll look at it in k-space. So I'll plot kx and ky. And so this mode this is just like a mode with a single k. So it starts off here in k-space, where the kx and ky have opposite signs, so they're in this quarter. As the shear acts, the distance in the vertical direction, or this is like really the azimuthal direction, as the shear acts like this, it stays constant, right? This is the same as this, because it's just being sheared like this. So the ky is constant. So ky is constant, but kx, here kx is that you have an infinite wavelength in the x direction, so kx goes to 0. So it goes through kx equals 0, and then it just travels off like this. Right? So the mode just travels like this in k-space. And its amplitude, its vorticity, is constant as it's swinging in k-space. And, well, we can work out what the speed is of how fast it's moving in k-space. We just set omega goes like e to the I kx of t times x plus kyy. And we stick this into here, and we get kx dot is equal to q ky. Right? The x term cancels this. And so we have kx is equal to q t ky. So when ky is negative here, it travels off to negative infinity. When its time increases, kx goes to negative infinity. If you start off here, it goes off in this direction. So basically, this is dynamics in all of k-space, except there's a special place in k-space. There's this line here, the ky equals 0 line, where ky equals 0 means kx is constant. So what this is, these modes with ky equals 0, these are axisymmetric modes, where the phase fronts, well, I'll draw it in here. So the phase fronts here look like this. So they're exactly aligned with the background shear. So the background shear doesn't do anything to it. And really what this mode corresponds to is, instead of having a linear shear across the box, like at the top, we just sort of change the shear profile slightly. And it's just 0 frequency, so it just stays there forever. And then I can also draw the phase fronts in here. So this here was a leading mode. As it swings here, it becomes a radial mode, or the phase fronts point in the radial direction, and then it becomes trailing. Okay. So again, this seems pretty simple, but there is one interesting aspect of this picture, which is I said that the vorticity is constant if you follow the amplitudes of any of these modes. But something interesting happens if, instead of looking at the vorticity, we look at the velocity field. So we look at u. So let me do it here. I said omega is equal to del cross u, so I was just replacing del's with k's. I'm not being careful with the i's. we have omega is k cross u. So that means that, and I also know that k dot u is 0. So we can write u is equal to k cross omega over k squared, right? Because then k dot u is 0, and then it returns this. So we have u sub x is equal to k sub y times omega over k squared, which is ky squared plus kx squared, right? And kx squared is what I said before. Kx is now the swinging kx, so it's qt ky. So this changes in time. So what we see is, let's say we start off with a mode way out here with large kx and some fixed u sub x. Then as kx swings towards the radial direction, this becomes very small, right? Here, this becomes very small. So the velocity becomes enormous. It can become very, very big. It can become arbitrarily large depending on where we started out. If you started out increasingly here, then for a given u sub x, you get an arbitrarily large amplification. So I can also plot it on here. If I plot versus kx, if I plot u sub x, the amplitude of the velocity field, then it goes like this, and it becomes hugely amplified over here. But then again, it decays away towards 0. So this transient amplification, people have noted for a long time, and people have said this might be very interesting. Maybe this is what leads to turbulence. If you can have these enormous amplifications, maybe we'll have some nonlinear coupling between modes, which can lead to the magical transition to turbulence, which people have been looking for a long time. And this speculation has been around for at least since Orr in 1907. And also it's recently become popular in astronomy, in accretion disks recently. People have looked at the transient amplification, seen it gets amplified to huge values and say, oh, this could be really interesting for turbulence, or it could be really interesting. But really, to go any further, so this type of arguments is relying on some sort of nonlinear coupling between modes. But the question is, how big do you have to be to couple nonlinearly? And what are those nonlinear couplings? Are they interesting, or do they lead to turbulence? So that was sort of my line of approach to this problem, was to look at the nonlinear coupling between modes and see if anything interesting happens. Okay, so I'll describe now a bit about the nonlinear coupling between the modes. Okay. So if we can just go back to k-space. So in k-space, we have all different kinds of modes. We have swinging modes, we have axisymmetric modes. It turns out that the most interesting couplings are between a swinging mode and an axisymmetric mode. I guess I'll draw it again here. So this is kx, and this is ky. So we have an axisymmetric mode here. Remember, this is just a zero frequency stationary mode. I'll draw its phase front here. And I'll call this the mother mode. It's one of the parents in the coupling story. And then there's a father mode over here, which swings off to the left. So by just linear analysis, it goes here with constant vorticity, and this stays here with constant vorticity. And I'll draw its phase fronts here. It's leading. Okay. And so for what happens with nonlinear coupling is this mode couples with this mode, and they make or I'll call this the father. So the father couples with the mother, and they produce a son whose k is the vectorial sum of the parent's k. So it produces a son over here. Right? So as the father swings along, it continually couples with the mother and produces a son behind it. Okay? So this seems like it could get kind of complicated, because not only do we have the usual nonlinear mode couplings, we have all this swinging around in k-space. But it actually turns out that there's a very nice simplification that occurs, which is that the father basically doesn't couple with the mother at all until it reaches this position. Just as it swings right through this position when its phase fronts are radial. And the reason for this is that the most important, the reason for this is really just this transient amplification that I was talking about. Because of this transient amplification, all the effects of the father are concentrated right here when it crosses within 45 degrees, when its phase fronts cross within 45 degrees of the radial direction. So what happens is, let's consider the case, for example, when the mother has a fairly large amplitude compared to the father, still small in absolute value. But so what happens is the father travels here. Then he couples with the mother over here, and the son by that time is over here. Right? The son is trailing behind. So they produce, basically all at once, they produce a son over here. Well, not over here, but right on top of it, right over here. And the son can swing along. He can couple with the mother, even though that's not very appropriate. But the son couples with the mother, and they can produce a grandson over here. And so you can have this loop continuing. And so you see in this type of picture, there is really one important question which we want to know, which is the son bigger than the father? Right? Because if the son is bigger than the father, then the grandson will be bigger than the son, etc., and you'll have a runaway growth, and it'll be an instability. But conversely, it'll be stable. Okay? So what I'm going to do now is, so we can work out what the amplitude of the sun is. So we consider the case when the father is here and is coupling with the mother, and they're going to produce a son. So first, I'll show you the cartoon way of what happens. Is that when the father's phase friends look like this, its velocity field is aligned with the phase friends, right? Because it's incompressible, so k dot u is equal to 0. So its velocity, so it gives a velocity field like this, and it acts on the mother, whose phase friends look like this. So what it does is it pushes out the phase friends here, pushes them that way. So it turns the mother into this, right? So it distorts the mother. And you can decompose this into a leading wave, which becomes the sun, and a trailing wave, which just goes off to infinity. It's not important anymore. Okay, so we can do this. So since we want to know how big the sun is compared to the father, we should do this quantitatively. And so the important nonlinear coupling term, the nonlinear coupling is just u dot grad omega. It's the rate at which, the rate at which the vorticity is advected. And the important term for what's advecting what is that the u is supplied by the father and the omega is supplied by the mother. So let's just put in the u for the father. So ux, I'll evaluate ux for the father dot grad omega for the mother. This is the change in omega is equal to this per unit time. But then I also said this acts over, it's basically only in the time when the father is amplified. So it's right around when it's near its maximum amplitude. So it's just one shear, it only acts for one shear time. So the time at which it acts for is just times 1 over q. Okay? So then this is equal to, so ux for the father. So here I had ux here for swinging mode. And I'm taking it when kx is equal to 0. Right? I'm evaluating ux over here. So it's just this. It's omega of the father. And when kx is equal to 0, this is divided by ky. I'm not being careful with signs or i's or stuff like that. So it's omega father over ky. And then I'll also put in its spatial dependence. Right? The father it's a sine wave like this, so it's cos kyy. So here ky refers to the ky of the father as it's swinging around like this. And then I'm using it to advect the mother, so dot grad of the mother. And the mother is omega m times cos kxx. Right? It's some kx, and so kx now refers to the mother and ky to the father. So just I won't put subscripts on them. And the dot grad is a dx, right? Because the mother only depends on x. Okay, so what we have is this is equal to this is the omega father times omega mother. When I take the derivative, I get a kx here, and I have a ky here. And a 1 over q over here, which I didn't put in. Over q ky. And then I have a cos kyy and a sine kxx, which I can write using these sum and differences. It's basically sine of kxx plus or minus kyy. It's the sum of two terms like this. Okay? So it's basically a sum of a leading wave and a trailing wave. And the interesting thing is this coefficient. So we took the father mode, and this is now the amplitude of the son's mode. So the son's mode, omega son, has amplitude, it's equal to omega father times chi, where chi is this. Chi is equal to omega m kx over qky. Okay, and this is actually, it's pretty interesting and sort of surprising, the form that it takes. So what's especially surprising is, let's consider a mother mode. So the mother's just, remember this is, omega sub m is the vorticity in the mother mode, and omega sub m over q is her vorticity divided by the background vorticity. So we can consider a small amplitude mother mode, where this is tiny, let's say 10 to the minus 3 or something. But even if this is tiny, we can still make chi to be bigger than 1, as long as we take ky, the father's ky, to be very small compared to kx. Right? That will make this bigger than unity, and so we'll get an instability, even for for a mother mode of infinitesimal amplitude. It will become unstable.
Are you saying that the total vorticity of your system is kind of blowing up?
No, the vorticity is constant. It's coming from the mother's vorticity. Right, I mean, you can sort of see it from this equation.
Yeah, sure. So I'm confused.
You mean vorticity or entropy?
I mean stuff.
The vorticity is conserved even point by point. Like,
so this chi coefficient is taken from the mother.
it's taken from the mother, right? So like in real space, what happens with this instability? Well, I'll show you the movie in a second. But, so let's take, if we put a mother mode into a box. So I'll draw. The mother mode's contours of constant vorticity. And so the mother mode has a characteristic omega sub m over q, which is her amplitude, and a ky. And a kx. Right, kx is the kx of the mother. So there's a characteristic omega sub m, where there's a value over q. So now let's say if we choose the box to be if we don't choose the box to be big enough, or let's say for some ky, let's say if we choose a box so that all the ky's are so big that this is always less than 1. Then if I start off with the mother mode like this, with a small amplitude, then this mother, and I put in a whole bunch of perturbations, what will happen, all these perturbations will die away, and this mother mode will just live. But if I make the box a little bit bigger, so now the ky, I'm allowed a ky which is sufficiently small to make this bigger than 1, then what will happen, it'll look dramatically different. If I start off with a mother mode like this, basically the perturbation will grow, with the small enough ky will grow, and it'll form into a sort of a vortex, which is hard to draw, but something like this. So basically what the instability does is it just reorients the mother's vorticity, and it forms a vortex. And before showing the movie, I'll just say one more thing, which is that so this type of picture also connects with the usual pictures of vortices and shear flows. So there's a famous solution called the Kita vortex. If you have a shear flow, and we have so Kita vortex is a vortex of constant vorticity of little omega, and if the perturbed vorticity, if the vorticity in the vortex differs by a small amount from the outside vorticity, and the vortex is weak. So the weaker the vorticity in the vortex, the more elongated it is by the shear. If the shear tries to just stretch it out. So the elongation is related to the strength of the vortex. And the way it works is that the width of the vortex, if this is the width and this is the length of the vortex, so the Kita solution is that Lx over Ly is equal to the strength of the vortex, omega over q. So the weaker the vortex, the more elongated it is.
So this is an inelastic solution?
This is incompressible.
It's a compressible solution, but I think if you include compressibility, that solution will not be valid anymore?
Well, I mean, I assume that it depends on, I assume that there's a parameter regime where the incompressibility is a good approximation. And so typically it's said typically, as long as things are weak, as long as motions are subsonic, then the incompressibility thing works okay.
You just have it on a sufficiently small scale.
Sorry?
Just make the thing sufficiently small scale,
Right.
so the flow is very subsonic.
Exactly. Yeah.
You just contract the spatial dimensions of your thing enough, and it'll work.
Exactly. Okay. But yeah, so the point I wanted to make is that this is basically the same as my chi, right? It's basically setting my chi equals to 1. If I just replace ky with 1 over ly. So in other words, if I start out with a situation with chi bigger than 1, like in this situation, chi bigger than 1, it becomes unstable and it settles down to a vortex such that chi is a Vort unity. So it's a natural way to stabilize this instability. Okay.
Yeah, so if the instability is taking vorticity from the mother and putting it into
It's reorienting the vorticity.
consideration, yeah.
Mhm.
So I mean, for it to be an instability, don't you then have to replenish the mother as well to keep it going?
Well, it's not it won't lead to a steady state. I mean, what do you mean to keep it going? I mean, the instability ends
You're
when the
just
mother is destroyed.
redistributing things,
That's
not
right.
generating.
That's right. The vorticity, that's right.
Yeah, what is the vorticity distribution of the, if you regard the initial configuration as being the background shear plus your axisymmetric mode, then what is the vorticity distribution of that initial configuration?
You mean, what does the vorticity look like? I mean, these are just contours of constant vorticity, so it's just aligned like this.
Yeah, but I mean, the thing is, isn't there something called Arnold's theorem, which says you have to have an extremum? I mean, this is a two-dimensional flow, from what I'm
Oh
calculating.
yeah, so there's an
Two-dimensional incompressible flow. So you
Mhm.
to get any kind of even not to get a non-linear instability, don't you need an extremum in the vorticity?
right. So I do have an extreme in the vorticity. So if I plot,
I was asking.
okay, sorry, I didn't. So if I plot vorticity here, then basically the background vorticity is minus q. And if this can be interpreted as a sine wave, in which case it looks like this, or it could just be a step function, in which case it just looks like this. But yeah, it's true. You need a
So you need to put a background axisymmetric mode which is big enough to change the vorticity profile so it has an extremum.
well, the background vorticity is just constant.
Yeah.
So it could be an infinitesimal mode. Like the vorticity could be tiny. The only thing that's required for the instability to go is that this is bigger than 1. So omega over 2 can be tiny.
But isn't there more? I mean, you actually need to have an extremum in the vorticity profile.
But the background is only uniform here because it's in the shearing sheet.
Right. So it's true. It has to overcome the pressure forces in real life.
I mean, you have to. I mean, that's a non-trivial business, right? You start with
Yeah.
background shear. You have to put something on it which makes the vorticity profile have an extremum.
But in the shearing sheet, basically anything will make it have an extremum, right? Because
that's a limitation of the shearing sheet.
That's
There's no
right.
vorticity gradient.
That's right. So I mean, there's CS squared over Keplerian, CS squared over V Keplerian squared terms. So in real life, it has to compete with that. So that amplitude is sort of like 1 part in 1,000. So I mean, there are limits, and yeah.
Well, it's the same thing as the fact that there are no Rossby waves. Well, there may not be Rossby waves in a real disk either.
Okay, I'm not sure.
Yeah, I think you're right. It's the same, which makes the Rossby wave instability.
So basically what you
Yeah,
have
because
here
of
is a
this
kind
is
of
an extreme
Kelvin-Helmholtz instability of non-axisymmetric waves, and you find the classical criterion for the Kelvin-Helmholtz instability, which is basically that the unstable wavelength has to be larger than the width of the vorticity structure you have.
No, well, but it's multiplied by the amplitude, so it has to be larger, significantly larger. So so this is basically you can take the results in the classical texts on fluid mechanics and derive these things. But what was especially surprising for me was that even if you take a mother mode, an axisymmetric structure that has arbitrarily small amplitude, it's still going to be unstable to long enough perturbations. So, okay. Okay, is people buy that? I mean, I don't know if yeah, it might have been obvious to other people, but I mean, I think also it gives sort of a nice dynamical way of seeing how vortices form. So people have done simulations in 2D where they start out with just sort of random vorticity distributions, and they see vortices form out of it, and they just sort of wave their hands and say inverse cascade of energy in 2D. And I think this sort of shows how the vorticity moves around to form these vortices. Okay, but so this is all everything I described with 2D. Of course, the real interesting question is what happens in 3D. So here I'll show a simulation, 3D. So I have to describe what I do. I'll just let it run a bit. I'll start so first of all, these two movies are from the same simulation. It's just on the right-hand side, I cut out the stuff from the outside so you could see the stuff on the inside more clearly. And okay, so in this case, I showed the so I showed the orientation like this. So this is the radial direction, this is the azimuthal direction, and this is the vertical direction. Okay? So what I'm starting off with is this is an axisymmetric mother mode, right? It's aligned with the background azimuthal direction, and the color code shows the vorticity. So this one is a sine wave in vorticity, and then the amplitude of the vorticity that I choose. You can't really see the colors, but it's about 1 part in 10. So the vorticity of the mother mode relative to the background mode is about 1 part in 10. So it's a small amplitude mother mode. But we wanted to show, first of all, is to show that this mother mode can be subject to this 2D instability and wrap up into a vortex. So what I had to do is I have to choose a box which is long enough, which is about 10 times longer in the azimuthal direction than in the azimuthal direction and the radial direction by about a factor of 10. I've chosen a factor of 15. And I should say I've blown up the scale in the radial direction by a factor of 5 so we could see things. Okay, so because I've chosen this to be sufficiently long, therefore it will be subject to this instability that I just talked about. And it'll roll up into a vortex. And we can see that it does. So it rolls up into a vortex. It's easier to see here. You see there's a vortex forming. Of course, the vortex eventually decays, and that's because there's some viscosity in the code. So in the limit of 0 viscosity, one would expect the vortex to live for a much, much longer time. And I also point out that in this case, I don't know if you can see, but I also initialized with these vertical perturbations. You can see that it's not vertically symmetric. And these vertical perturbations, they die away after I let it run. So it's stable to these vertical perturbations. So the basic idea for what I'll argue is that the reason that as long as the height of the box is less than the width of the vortex, then the vortex can live for a long time and vertical perturbations will die away. But if you make the box too big, then you have a different behavior. Okay, so I'll just say, so in this case, in this case, note that I've chosen the height of the box to be a little bit less than the length of the box. So in this case, one would expect it should behave well. Well, first I should say, if you take a vortex, like a 2D vortex, and put it in a very, very thin box, intuitively one would expect that vortex would live for a long time, and 3D effects would allow it to be stable, would allow it to live for a long time. But as one makes the box bigger and bigger, then 3D effects can start taking over. And so in this case, where I've chosen the box to be a little bit smaller than the length of the box, then you see that the vortex is indeed stable. I mean, there are issues with resolution, which I'll describe later. Okay, so here all I've done is this is the identical simulation. I'm starting out with an axisymmetric mother mode, but now I just make the box bigger in the z direction, and I'll let it run. Oops. So you see here it becomes violently unstable, and right away it decays into some sort of turbulent state. And I should say that the time scale, it goes to like 1,000, and that's in units of orbital time. So we have this turbulence that lives for hundreds of orbital times, and eventually it goes away. I mean, it's by no means self-sustaining turbulence, because I started off with this axisymmetric mother mode, and it's just feeding off of that. And this is what's happening as the mother mode is decaying, but you get some sort of turbulent state. And then I'll just show from that simulation. I'll just show from the turbulence simulation, because turbulence is interesting, right? That's one of the reasons why we study hydrodynamical disks. So I'll plot the energy in turbulence simulation. So this is versus time. This shows the u squared energy. Basically, it starts off small, and then it gets very large. It gets much larger than it was, about sort of 4 or 5 times amplification, and it stays large and positive for a long time before eventually decaying for sort of hundreds of orbital times. And another interesting thing to compare is the other components of the energy budget. So this is the energy equation, which says how the change in u squared, remember u is the perturbed velocity, so the change in the perturbed energy is driven by 2 terms. There's this ux, uy term. This is the rate at which shear is pumping energy into the perturbation. And there's this viscous term, which it damps away. So to compare these terms, I wanted to compare them at u squared, so I took the time integral of this, so I could compare with u squared. So I have the time integral of this ux, uy term, that gives this, and the time integral of the viscous term, which gives this. So the first thing to note is that if I sum these 3 terms, then I have exactly 0, so it shows that the simulation conserves energy, which it should. But more interesting, this is delta E shear. So this ux, uy is the outwards transport of angular momentum. And this is really why people want turbulence in the first place, because what turbulence does is it transports angular momentum outwards, which then allows a disk to accrete. And so since the time integral of this E shear rises linearly with time throughout the turbulence, what we see is this ux, uy is positive and constant. So this turbulence is doing what it's supposed to do, what we expect it should do. And it's transporting angular momentum outwards. Okay. Okay, so that's it for the movies. So then there's one last thing I wanted to just describe, which was the transition. So I showed these 2 simulations, one in a short box, one in a tall box. And so to give an explanation for why it is that the short box has a long-lived vortex and the tall box, the vortex decays. And why is the transition when the height of the box is equal to the length of the vortex? So we can look at that in a way similar to how we looked at the 2D instability. Okay. So what I'm going to do is I'm going to look. So before I was looking at the couplings between 2D modes, between modes in the kx, ky plane. Here, I'll draw kz, kx, and ky. So just to remind you, before there was a mother mode over here, the mother mode here. And then there was the father mode was swinging along here. This is all with kz equals 0, so in the 2D. The father mode was swinging along here. And when it reached here, it could couple with the mother mode and create a sun, and this is what led to the Kelvin-Helmholtz instability. Okay. Okay, so now we want to see how do the other modes behave in k-space, these 3-dimensional modes. So let's first look at the kx, kz plane. So I'll set ky equals 0. So this means when ky equals 0, these are axisymmetric modes, right? They have an infinite wavelength in the azimuthal direction. So let's just look at the kx, kz plane. Okay, so let's first consider modes up here. So it might be easier if I draw it. So let's say the plane of the disk is like this. What these modes have, they only have kz, so the phase fronts. If my hands represent the phase fronts, They're aligned with the plane of the disk. And what these modes do is they just oscillate with the Keplerian frequency, just with frequency capital omega. Right? There's nothing to resist the epicyclic oscillations. So they have frequency capital omega. And I can draw, if we look down the edge of the disk, the phase fronts look like this. Right? And they're just oscillating like this. And then what happens is these oscillate with the epicyclic frequency, and then as you rotate the phase fronts, but keeping things axisymmetric, then the frequency drops. Well, if you rotate like 45 degrees, nothing much happens. But then once you rotate it beyond 45 degrees, as you go in this direction, then it drops to 0 until we reach this limit, when the phase fronts look like this, and then this is just our old mother mode, axisymmetric, with 0 frequency. When the phase fronts are more than 45 degrees to the horizontal, up here, the frequency is capital omega. And down here, it just drops off linearly. The frequency is kz over kx. But here it's capital omega, and these are lines of constant frequency. It's just the frequency gradually decreases until you hit kx, until you hit this phase fronts like this. Okay? So this is how these axisymmetric modes behave. But really what we want is we want to understand how these swinging waves behave, like an arbitrary mode. So let's say a mode up here. So we want a mode up to understand how the mode up here behaves. So it has a kz, it has a fixed kz in ky, and it's swinging along in kx. Right? So it's swinging along in kx until it hits here. And so basically we can understand the behavior of these modes by taking into account that there are basically only two important effects. There's shear and there's rotation. So there's a characteristic time scale of a mode up here, the shear time, which is the time for this mode to swing around to point in the radial direction. So there's the shear time. And remember kx was equal to qt ky. I think I just erased it. So that's the rate at which a mode swings along in k-space. So that implies the shear time is equal to kx over qky. And then there's an oscillation time, which is the epicyclic frequency, the time for it to undergo its epicyclic frequency. And so that's given by this frequency, as long as we're in this part of the plane, right? As long as the phase fronts are close to vertical. So there's an oscillation frequency, which is 1 over this, so it's kx over omega kz. Okay, so now we can sort of see what happens to modes, all of these swinging modes. We can label any swinging mode by where it pierces this kz ky plane. Right? And there's two limiting behaviors. One is when kz is less than ky. Kz is less than ky. Then the oscillation time is very long, and the shear time is short. So basically it's just swinging around, and basically it's just behaving like a 2D mode. So these modes over here, if kz is closer to here than it is to here, then it's just like a 2D mode, and it's just swinging around, and it'll undergo transient amplification. So that implies kz less than ky, implies the shear time is short. Less than t oscillation. And the opposite limits, when kz is bigger than ky, then the epicyclic oscillations are faster, and this prevents transient growth. So basically, so these modes just basically oscillate around, and so these modes are living way up here. And they oscillate, and there's no transient growth. So they can't support this type of feedback loop. Remember that we had in the kz equals 0 plane, where we generated the vortex. Modes up here can't support that because they don't reach large amplitudes. So that implies that the shear time is bigger. Okay, so now we can sort of have a cartoon explanation for why the vortex in the tall box decayed into turbulence, and the vortex in the short box, it lived for a long time. Okay, so let's consider first the tall box, which decayed into turbulence. So in the tall box, we have many modes with small kz. Right? So we have many modes out over here. So let's consider a mode in here that fits in the box. So if we consider the modes down here, they behave just like the 2D modes, like the modes over here. And so if this mode is unstable to form a vortex, then this mode would also be unstable. So this father mode, it goes here. When it reaches here, it couples with the mother, and produces a sign over here, and it'll also support an instability. And so you'll have these, many different KZs will have different instabilities. And this is what leads to the vortex decaying. Then as you go to much larger, as you shrink the box, if the box becomes very small, and in particular if the KZ if it's become so small that the only KZ that will fit in the box is larger than the relevant KY, right? Then all the modes will oscillate and they don't support this instability. So these modes will be stable and then you're left with a long-lived vortex. So this is what I have in my paper. But I should say this, so Geoffroy and John have a paper where they look at modes which I didn't consider, which is, if we consider, so this is in the short box. So in a short box, the lowest non-zero KZ is way up here. If you choose Kx and Ky, which is comparable to the Ks of your vortex, then those modes will be stable. But you can still go to extremely high K modes, so way out in this direction, where the Ks are much larger than the K of the vortex. Basically, if I let's say take a vortex and I put it in a thin box, then the Ks, I have to go to a much larger K, which is of order the ratio of how much the box is less than the length of the vortex. But these large Ks are also unstable, or maybe pictorially. If I start out with a vortex like this, then it's unstable to very, very high K modes. And so this is interesting, and I guess it remains an open question what happens to these modes with very high K. I'm not sure if you want to actually destroy the vortex, you want these extremely high K modes to back react onto the parent vortex, which has a much lower K. So it's not clear that these modes, even if they go unstable, if they'll really destroy the vortex. But this is all for future work, okay, thank you. Yes?
I have a question, I have many questions. The first one is in the classical picture of the electrical instability, which was described by Gladney in 1986. The resonance which leads to the electrical instability is not the one you are describing here. It's a resonance between these epicyclic motions you are talking about, so this Q omega thing, and the turnover time of the vortex. In your picture, there is no turnover time.
The turnover time is the shear time.
No, it can't be.
What do you mean?
Turnover time, it's a turnover time, it's not the shear time. You can have a very long vortex and the turnover time will be like 1,000 shear time.
Well, so a vortex is characterized by this relation, right? So the turnover time is 1 over little omega.
And then 1 over omega can be very small compared to
or large.
Very large compared to
That's right. And if I take the Kx and Ky to be characterized by the length of the width of the vortex, then that gives the same thing. This will be 1 over omega. If I take the Kx and Ky to be comparable to the Kx's and Ky of the vortex, then it will be the turnover time. So I'm saying, so I think this is appropriate when the Kx and Ky is of order the Ks of the vortex.
It's not true. If you're on a streamline and you have a free particle and you follow this free particle over one turnover time, it's not going to be omega times Kx over Ky. It's just omega.
Well,
you have one free particle on a streamline and it just do one turnover.
It's independent of K, right? The turnover time doesn't depend on K.
The turnover time is the property of the vortex.
no, I understand.
It doesn't depend on the
But
scale.
I mean, this argument is for the Kx's and Ky's of order the K of the vortex. So it's the same as the turnover time. I mean, this is.
No, it's not. It should not depend on Kx over Ky. I have a big vortex. It doesn't have to be in a shear fine. You can say you have a cyclone. In a cyclone, the turnover time is given. It has nothing to do with what's happening outside, and it's not related to the scale.
I think you're talking about different things. What he's talking about is a parametric resonance. So the fluid, as it goes round, it has a natural period, which is its turnover time. It's just a property of the equilibrium. It doesn't depend on any of these Ks. Then what happens is that you have a parametric resonance between that period and the epicyclic oscillation. So if you, I mean, essentially the inertial modes, which what the epicyclic oscillation is, sit on the streamline, on the particles on streamlines as they go around.
Mm-hmm.
And they get parametrically excited. Sorry?
They oscillate while they rotate.
Yeah.
And you want
Yeah. I think it's a different. It sounds different to what you're describing here.
It seems here that your resonance is between this epicyclic frequency and the shear time, as you say.
Well, it's the shear time across the whole vortex. So it's the time for the, it's the shear time using the kx and ky's of the vortex. I mean, if you went on where the kx is of order the 1 over the length of the vortex and the ky is 1 over,
Yes.
so like if you consider, yeah, well, and we could consider other k's. I mean, you're saying there's certain k's where I would say there's an instability and there's not an instability?
I'm just saying that if you have one perturbation, whatever is its wave number, and whatever is the size of my vortex, you have a closed streamline, and this thing is going to travel on the streamline and get back to its original point. That's a turnover time.
Mm-hmm.
I don't see here where is my turnover time. I don't see how a perturbation is going back to its original state after one turnover time.
Well, I mean, in this, like in the 2D, if you just look in the kx, ky plane, then well, it's sort of like this picture. Right, so if this is the typical ky of the vortex, well, if let's say we start out with an axisymmetric mode, then what will happen is the father will continually making the sun, and then you'll be left with a steady state where their father modes traveling along here, producing mother modes like here. So we'll have a vorticity distribution like this. And so the k's will be rotating on the 1 over omega time scale. But the time to go from here to here will be avoided 1 over omega.
Are you keeping the mother mode is staying there, or
Well, so
vortex doesn't have?
you mean when it becomes? You say when it becomes nonlinear. Well, what happens when it becomes nonlinear is the mother actually doesn't changes sort of by order unity. So the father feeds off the mother until it sort of takes half the mother. Well, it depends a little bit, but it sort of takes half the mother and it just sets up and all this like this, where the k's just go around. Right. And where were you thinking the mother mode's vorticity is going?
Well, it depends how you put your. I mean, how do you envisage a key to vortex, for example, in the shearing box? Because there's an issue with that.
Why are you saying
Unless you
that?
change the background.
I mean, you can just. I don't see why. You're saying because of boundary conditions? I mean, we could just take like an enormous shearing box and put a vortex like this, and then the image will be over here, and it doesn't. I mean, as long as like the length of the box is longer than the length of the vortex.
But are you saying there is an axisymmetric component to this? I mean,
Yeah. Well, sure, there's an axisymmetric component. Right. If I integrate along here, then the total vorticity will look like this.
Right, but if you're making the box arbitrarily large, then
Well, relative to the box, but I don't think it's important. The relative value.
well, okay, that's a side issue. But I mean, I agree that I don't see the elliptical instability.
Well, I mean, it's similar in the sense that when there's if you focus on the k's that are ordered the k of the vortex, then you get the instability when the turnover time of the vortex is of order the oscillation frequencies, which is similar to the elliptical instability.
How do you describe this instability?
How do I describe?
I wasn't clear how you're describing the instability you're talking about. I mean, how does it happen, the instability? I mean, the elliptical instability has a clear description of what's going on. Whereas what you have.
Okay, so I have a more quantitative description. So I have a description for the 2D, for the instability in 2D. If I start out with the mother mode, I can say what the criterion is
In 2D.
in 2D, right?
What about
And then, so for 3D, then for these modes, I can work out the couplings between this mode and the mother mode, and it produces a new mode over here, and I can see what the criterion is for this mode to be stable or unstable.
But the mother mode is the original axisymmetric
That's right.
not the vortex.
No, so I mean, this is the
So
instability
you're
for,
actually looking at the stability of the vortex.
right, I'm looking at the original axisymmetric mode.
Right, so I think that's the difference. I mean, what Geoffroy is talking about is the stability of the actual vortex
But,
once it's formed.
but I mean, I think the behavior, so, okay, in my experiments,
Mentioned about that already.
I mean, in my,
The actual vortex involves a zillions of K, because there's
No, but there's no,
X dependent.
but there's no turnover time for an axisymmetric.
No.
A ridge, right? An axisymmetric is just a ridge. It's like the vortex.
No, but you must have in this picture you have a whole family of modes with
Just
kx.
to
I
describe the
mean,
vortex.
it's just a nonlinear solution, so you can't have just one. You have a whole family of these guys, so that the Kida vortex is a steady solution in the infinity node box. So it has to be a steady solution in your Fourier representation, which means that it's full of modes everywhere.
right, so let's say if we start out with, instead of starting out with just an axisymmetric mode, we could start out with a Kida vortex, and we could plot out its vorticity distribution in K-space, right? And so then I would guess that it, I mean, I mean, you know what, the contours in K-space will just, of constant vorticity will just look like this, right?
But the turnover time is well defined. In a Kida vortex is just 1 over omega. So the turnover time should be well defined in your representation.
Right, well, so in this, so here I'm plotting in Kx, Ky space. So then the turnover time is just the time for any K to go from here to here. And it's always, because in the Kida vortex, where the aspect ratio, where the Kx over Ky is the same for all Ks, then the turnover time is, this is 1 over omega, this is 1 over omega. So it's, all of them have 1 over omega.
So we have excited a bunch of wave vector in K space. So now I can couple with any of these with my vertical modes, because I have all these guys everywhere, even at very large Ks.
That's right.
So
I think that, so there are, so I mean for this K, so what I was doing is relevant for the Ks of order the K of the vortex. And I agree that there are Ks out here that will couple, I mean I agree with you. And I didn't consider those. So I should have considered modes out here, but modes out here that will couple with a background vorticity, so it will couple out with modes over here, but I didn't consider those.
right. So my conclusion is basically that if you have a vortex meaning a steady nonlinear solution in which you have all these modes everywhere, then with your analysis, you can't say that this vortex is going to be stable if you remove the small kz. That's my conclusion. You can't say that this vortex is going to be stable if your box is small enough in the vertical direction. Because as you said, you don't consider the modes which would be unstable.
Well, but I mean, obviously I should have considered the modes that wouldn't be unstable. But
I mean, if you want to say that they are stable, you should consider all the modes which can be an instability.
No, I agree. So I should consider those modes also. So I guess my conclusion, from what I've done, I mean, it was before you wrote your paper, but my conclusion for what I've done is if I'm looking for modes whose Kx and Ky are of order the Ks of the vortex, the background vortex, those will be stable in a small box. And it's true, if you have to go to much, much higher K.
But you can't conclude that on what you've presented.
Well, I didn't, so that's right, I didn't, well, no, the second part I didn't do. I mean, the second part I'm basing it on.
It's saying that basically if you consider the waves which have the size of the vortex, you can say something about their stability in this analysis. But the point is, if you want to say something about the stability of this thing, you have to consider all the possible waves, not only the waves which are the size of the vortex. And my point is that, for example, the elliptical instability is scale invariant. And of course you don't see it, but this elliptical instability is known to destroy any elliptical vortex in nature, and there are experiments showing that. So
well, it's not. I mean, it's not clear for in this case what will happen if there are only the very high K modes which have become unstable. It's not clear if those will destroy the vortex.
But if you look at the experimental results, it seems that in the end this thing modified. I mean, you get back to a circular vortex in the experiment.
You're talking about rotating.
No, you start with an elliptical vortex like that.
But this is in a rotating box.
It does not have to.
Well, but that makes a big difference whether it's in a rotating box. because the fact that it's rotating and pushes all the modes up to this high kz, so it pushes you out here until you can get modes that are unstable. So I'm saying,
Not really, but anyway, my point is just that this thing is scale invariant. And since you are considering a specific scale, which is a vortex scale, of course you miss the other scales. But from your analysis, you can't
I mean,
say
a real
that-
vortex isn't scale invariant. There's a scale of the vortex.
No, the instability is scale invariant.
Well, I mean, it's scale invariant. I agree there will be unstable modes at very high kx and ky. I mean, there is a scale. There's a characteristic k where it's smaller than that, it won't be unstable, and higher than that, it will be unstable.
So you can't conclude anything about the stability of vortices. You know that? From this analysis.
Well, so I haven't actually done the high k stuff. I'm sure I.
Yeah, so,
Mhm.
yes.
Okay.
Yes, you haven't done the other wavelength analysis. So you can't conclude anything about the stability of vortices.
Right, I agree.
Okay.
Well, looks like this might be the point to go for a coffee.